Hi, Pete.
Hi, Scott. What do we got here today?
We have a rotor kit. We're going to measure some imbalance on this rotating shaft here.
Oh, this shaft rotates,
Yeah.
powered by this electric motor.
Yes. And so we're going to measure the first order imbalance using a tachometer sensor
This
and
one
an
here?
accelerometer. Yep.
And this accelerometer. Okay.
Yes. And so that tachometer is set up with a piece of reflective tape there.
Oh, yeah, right here.
Yeah. And the important thing about that reflective tape is the leading edge of that reflective tape is going to mark our 0 degrees, or our 0 degree mark on that shaft.
Okay, so we can do everything relative there for locating the masses for this imbalance.
Yes.
All right.
Yeah, so we're going to take that tachometer signal and we're going to tee it off from the tracking channel or the tachometer channel in our acquisition system, and also use that in a data channel and run an FFT on it to get the phase angle.
Okay, so it's teed off. You got what into the first channel?
So in the first channel, I have the tacho input, and you can see it's also in our tacho channel.
That's the voltage. That's the voltage versus time that you see in the first channel.
Yes.
Got this outputs.
Yep.
You're going to use that for phasing.
Yes.
And then you got it also plugged into the tachometer to keep track of the RPM.
Yes.
Is that right?
Yes.
Okay. And then you're measuring the vibration over here on this accelerometer, and that's really a response to the imbalance, right?
Correct.
Okay. It's not the imbalance itself.
Correct.
Okay.
Yep.
Sounds good.
So we have that set up, and then the next thing we're going to look at here in the tracking setup is we're going to do an initial run or a speed sweep to look at the imbalance. So we're going to cut the first order and look at the first order, which corresponds to the imbalance, and see where it stands.
So first order is the response. First order is proportional to the imbalance in the system.
Yes.
It's rotating a little bit right now. I see.
Yeah. And I have it set up to run from 400 RPM to 7,000 RPM to see what we get.
All right, I'm ready to turn the knob to increase the speed, Scott, when you're ready.
All right, so I'll arm the system, and then I'll hit start, and then I'll hit start and go ahead and run it through that speed range.
Okay. Well, I see some vibration from the accelerometer there. It's getting higher and higher with speed.
Yeah, and we'll see how bad it gets as we go up to that 7,000 RPM mark.
7,000.
So we're getting a high amount of vibration.
I would say so. Wow, that really got up there as we went up in speed.
Yeah, and that makes sense, right? Imbalance is due to both the imbalance mass and the speed of the system there.
And it's the square of the speed.
That's right. As we increase the speed, you can see that vibration really starts to shoot up.
And if we want to reduce that vibration, what do we do next?
Yeah, so let's pick a speed to balance. If we look at this, our phase is pretty steady throughout the run. So we can pick any speed here. I like to pick something maybe in this range where we have a good amount of vibration to make the calculations a little easier.
Okay, 5,000 RPM sounds good.
Yeah, so now from here, we'll disarm and we'll go to Tools, Add-ins, and we'll pick this single and dual plane balancing add-in. And when we turn that on, we get a balancing tab.
Cool.
So I'll click on that balancing tab. And here we have some setup. So we already picked our balancing speed at 5,000 RPM, and we'll use an RPM tolerance of 20 RPM. That just is how well you'll be able to control it.
Okay.
And then we have our tacho channel and our phase reference like we talked about, which is that tacho input split into a data channel. And then we have the unbalanced target, and so you and I will go for broke. We'll try to get rid of all the imbalance here.
Sounds good.
And the way we have it set up is we are going to remove the test mass after each measurement step.
Okay.
The sense of rotation from where I'm looking at it is clockwise, so we'll use a clockwise sense of rotation for our angles. And we'll do weight splitting because we have 16 different positions on that disc there on the shaft.
Here I have the disc So you can see that there's holes every 22.5 degrees here.
That's right.
So that's the only places we could put masses. So the system won't recommend something where we can't put a mass,
That's right.
but it'll still balance it.
Yep.
Interesting.
That's correct. We'll hit apply. And then we'll just stay in this interface. I'll let you spin the shaft up to 5,000 RPM. and
How
we'll
will I
see it.
know when I'm at 5,000?
Yeah, we can see the RPM here, and when you're at that 5,000 RPM, this box will turn green.
That's kind of nice.
Yeah. Okay, so now that you're at that 5,000 RPM, we'll take some initial measurements.
So we're quantifying the base imbalance.
That's right. And we can take multiple measurements for repeatability.
Usually 3.
Yeah.
Normally you might take a little more averages.
Yeah.
But we're doing just 15 to make it a little quicker.
That's right.
All right, and we're done?
Yes. So we have 3 runs here, and it looks like our initial So we've done our 3 runs, Pete, and you can see that we have, for our initial measurement, an amplitude of approximately 1.2 Gs of imbalance at 26.2 degrees.
Okay, that was our baseline. So what do we
Yes.
do next?
So we'll click next step, and we'll add a known mass at a known location.
Okay, I have a little scale here for measuring the mass. And the idea here is by introducing a known mass, we can, the change in imbalance is known to us over the baseline,
Yes. So how much mass do we have there on the scale?
1.2.
So we're going to take that 1.2 grams and we're going to put it at 0 degrees. Because
Okay.
0 degrees is easy to find. We just line it up with our tape.
I got my tape here. I can put it there, so I just put it straight up here.
So there you go. We got 1.2 grams now at 0 degrees, a known mass, a known angle.
All right, we're going to measure the change in imbalance from baseline.
So we'll put that known mass at 0 degrees, hit next step, and now we're going to measure it at 5,000 RPM again. Okay, we have 3 runs, Pete.
All right.
And we have that measurement with our first test mass done. So now when I hit next step, it's going to calculate the balance masses. So an ideal mass to fix this would be 1.7 grams located at 278.8 degrees.
Well, that's not quite a multiple of this 22.5, right?
That's right. So we did mass splitting, and so it's giving us 2 masses that we can put 22.5 degrees apart.
Oh, that's kind of nice that you put that option on. And one of them is about 1 gram, is that right?
Yes.
And the other is about 0.75?
The other one's about 0.67. So
0.67. All right, I got a 1 gram, and where should the 1 gram go?
So 1 gram is located at 270 degrees.
Okay, so that's right. I got 0 degrees up here with my trial mass location.
Yep.
And then I'll put the 1 gram in.
So you got the 1 gram in, and now we'll put the smaller mass. It's approximately a half a gram at 292.5 degrees.
All right,
Okay.
now that that's in, it's important to, because you checked this, to remove this trial mass.
That's right. So in our software, we said that we were going to remove the trial mass, and that's what we need to make sure to do.
Normally a part wouldn't be produced with a trial mass already in it, huh?
That's right. And if you had to weld your trial mass on the part, you could keep it on.
Oh, okay, that's good to know. All right.
So we'll go back to that 5,000 RPM, and we'll go back to that 5,000 RPM, and let's do our verification measurement.
So we expect less vibration. Sounds like less vibration so far.
Absolutely. So let's take our 3 runs here. All right. So Pete, according to this verification measurement, compare that with our initial measurement. Initially, we had an amplitude of 1.24 Gs in vibrational amplitude, and we've reduced that with this balance procedure to 0.04 Gs.
So this accelerometer location is vibrating a lot less,
Exactly.
which is due to the fixing up, if you will, of imbalance.
That's right.
But we had done an order cut before. Here
Yeah.
we just did this at 5,000 RPM. It seemed better. Should we check it against the whole speed range?
Yeah, let's look at how we did across the whole speed range. So we'll go back to the run-up. And on the run-up, we'll drop in our initial measurement.
Oh, so you just go to Data Explorer there to find the original run.
That's right.
Should we make it red to let people know?
Yeah, so we'll click on this and we'll change the color to red. And we'll make it a little thicker.
All right, so that's the curve to beat, huh?
That's right. So we want to see if this new measurement comes in underneath this original measurement. So I'll arm it. And I'll start the system. And when you're ready, we'll go through that speed range again.
I see some green. So that's our current measurement. Oh, it's looking like it's under so far.
Yeah,
Curious as we get up there in speed what happens.
absolutely.
Still really low. Wow.
Wow, Pete. I would say we balanced this.
I have to agree, Scott.
And that's how you balance that shaft.
Awesome.